All right, so today we're going to pick back up with our stacks. Last class we went through and we coded the beginning part of it. We made a stack of what? Marshmallows? Fluffy marshmallows we made a stack of. I believe that we have completed the add method to our stack. What's it called when you add something to a stack? Push. Good. What's it called when you remove something from a stack? Pop. Pop. Okay, so push to add, pop to remove. We're going to do two things today. The first is we're going to finish the program, which involves us writing our pop method. And then I'm going to show you a couple examples of where stacks are used in actual games. Now I say actual games very loosely. The example, we might look at two examples, are very, very basic. They're games that are being made in a game design class. So they're not the next AAA game that you're going to see. But it should give you a good idea of how they can be used on a larger scale. All right? Because I don't want to overlook the practical use of these. Knowing how to use them is great, but knowing when to use them and in what situations they fit in is even more important. It doesn't do you any good to have a whole garage full of tools if you have no idea when to use them. Okay, so we're going to take a look at both of these today. All right? Any questions before we start? All right, when we finish today, I will take our classes and put them up on Canvas so that you can access them. And at the end of class, remind me to look at the syllabus. We have to adjust a couple things schedule-wise. All right, so if we look up here, we've got our three classes. We've got our linked stacked class. This is the class that we have for the data structure. We're going to create one instance of this class because we have one stack that we want. If for whatever reason we had a situation where we needed to keep multiple stacks of marshmallows, okay, or maybe comparing it to what you guys just did with your grocery store program, if we wanted to create a situation where instead of running a simulation for a single grocery line, if we had a grocery store that had 10 lines, then we would instantiate our data structure 10 times. Because we had 10 separate queues. Okay? And we'll get into later, we could keep a single structure that held all 10 structures, kind of like a two-dimensional queue, but not a queue of queues, but a list of queues or something along those lines. Okay, but we'll get to that later. For this program, we're going to create one instance of our stack because we have a single stack of marshmallows. The next class that we have is our marshmallow class. This is the object that we instantiate, and we're going to actually add it to our stack. It has a next reference that can reference another marshmallow object, and it also has a fluffiness value, simple int value that just helps us keep track of where that marshmallow is in the stack. Bless you. Okay. Our third class is our driver that we use simply to demonstrate how it all works. So first line of code, we're going to create an object of our stack. And then all that we have so far is a simple loop that goes through and adds 5 marshmallows to the stack. All right, let me run this once just so that we can see, get a visual reminder of what we did. So I'm going to run it in the canvas, let it create the stack first, and then we're going to go ahead and drag our stack and drop it here so we can see what we've got. I'm just going to go ahead and hit play. As it goes through, we see that items get pushed up onto the stack. Now, remember, new objects get added to the front. So 40 is going to get pushed down and 35 is going to go in front of it. This is the opposite of a queue, where a queue would add it to the back. All right? 55 is going to get pushed in front of 35. Those get moved down. And this process can repeat indefinitely. We set up a loop that's going to go 5 times So this is going to create 5 marshmallows. But again, I want you just to see the pattern of what's happening here. New objects get pushed down, get added to the front. Okay? Any questions on this? And again, not a lot of code to accomplish this. If we look at the push method in our stack class, it is a whopping 3 lines of code. We have more comments than we do actual. And one of them just updates the size. So very little coding going on here. For a process that looks rather complicated, at least when we first approached the idea of let's code this, it seems a little bit more difficult than what the code suggests. Okay, really easy stuff here. All right, so any questions on this? All right, so let's pop over to our driver, no pun intended, and let's write the method for removing objects. Okay, so we added 5. We can go ahead and remove a few. So if we say stack.pop, what that's going to do is that's going to remove one of the objects, or it will once we code it. Whenever you have a remove function, should you also return the object that you remove? It's an important question, because when you are using a built-in stack from another language or from this language, you need to know whether or not to expect to have it return. Okay, we're removing the object when we call pop, but does that also return the object when we call it? And the answer is yes. Okay, and the reason it does that is there's going to be situations when you remove something that you want to actually do something with it. For example, if we have a stack of bullets that we're shooting in a game. If I say stack of bullets, pop, it's going to remove one of the bullets, but I want access to the bullet removed so I can attach it to the gun and shoot it. Okay? A lot of times you need access to stuff. Okay? Now, just because we have it returned doesn't mean that we need to do anything with it. Question?
If we didn't do that for our program, is that an issue?
No, it's not. It's not a big deal if you didn't do that for your program, because once we remove a customer, we don't do anything with them. Okay? So good question there. And if you did return the customer that you removed from the queue, no big deal. And that's exactly what I was going to get ready to talk about. If we have a situation like this, where in your program you probably had like queue.dq, okay? And you might not have had anything else on that line of code. You just removed the object, just like we do here. Even though pop is going to return the object, do we have to do something with it? For example, doing something with it might be something like this. We have system.out.println stack.pop.toString, which would call the toString method of the object that we removed. So this would call the marshmallow toString method that we just popped off the stack. This is actually doing something with the object that we removed. If instead we just did this, is this okay? Is this going to crash us? No. It's fine. What does pop remove, or what does pop return? Or what do we expect it to return? A marshmallow object. Good. So if it returns a marshmallow object, what specifically gets returned right here? The memory address. Good. The memory address of where that marshmallow exists in memory. So all that we would have is just a memory address. If we don't do anything with it, it just goes away. Okay? Not a big deal. So we'll leave it like this. We'll pop it off and call its toString method, which if we look at the marshmallow toString method, it just outputs its fluffiness. Okay? So we'll say stack.pop. I'm going to put this inside of a for loop just so that we can more easily control. So we'll add all 5 and then remove all 5. Any questions on this code? So let me comment this. This is add some marshmallows to the stack. Remove all the marshmallows. So now that we've got the code written for what we want it to happen, now we have to go to our stack class and write the pop method so that we can actually run this. Let's go over to our stack class and write public marshmallow pop. So again, looking at the syntax here, public, we need to be able to call it from another class. Marshmallow, this is the return type. We are returning a reference or a memory location to a marshmallow object. Pop, in our method, and we pass it nothing. We don't pass it anything because there's no need to pass it anything. It's always going to remove and return the object that's front or top of the stack. So, if we think about what we want to happen here, we know we need to return and remove. And in fact, this code is going to look identical to the DQ method for our queue. Because in both situations, we are removing and returning that front object. Right? So here's what I want you to do. Take a minute. I would like for you not to look at your queue class code. This is a good opportunity to practice. Take a minute, maybe 2 minutes, and see if you can write this code yourself. I'll give you a hint. This would be a good practice for your test. Filling in. We're going to talk about kind of a side note right now. Your test, your midterm, and your final are divided into 3 sections. And we'll cover this in way more detail when we review for your test. We'll spend a whole class period reviewing. 3 sections on your midterm. The last section is a free response section. In the free response section, I am going to give you a partially completed class. Something similar to this, where I have a method, you know what the method is supposed to do, but there's no code in the method. And I say, complete the method. So what you are doing right now, and I do this intentionally, what you're doing right now is intended to give you an idea of what to expect on your test. Okay, so take a couple minutes and see if you can write the code to remove the top or the front element of a stack. Keep in mind, you need to be able to handle the different configurations of the stack, whether the stack is empty, whether the stack is one object, whether the stack has a bunch of objects. Ready, go.
Josh went to, I guess, the first time they didn't have big ones, right? Like, I don't know what to ask him. Do you know looking for software engineers? Yeah, this kind of stuff. If I get into software engineering or wanting to get into AI, yeah, this languages do you need to be proficient in? ITSC software developer, software engineer. Cybersecurity positions.
All right, take one more minute.
Most one will take care of you. They get paid 1.5, so they have to living is best company. Are you serious? Well, so I will get that way more. That's what I'm talking about. That's what I'm talking about. Because now, when she came here for a different. She would pay expense, living expense. And make it have this more prestigious than each year. And postgraduate job. By the time you got a job, like you have experience.
All right. So this is first thing we need to consider is what?
The stack is empty.
Right, the stack's empty. The stack's empty, we don't do anything. Okay, so we will code a quick check here to make sure that there's at least something in our stack. So a couple different ways that we can do this. The best way is probably to take advantage of our isEmpty method. So we will say, we put a comment and say, make sure the stack is not already empty. If is empty, so if it is empty, we can do a couple things here. The first is a suggestion to print out a message that says, hey, you're doing something that you shouldn't be doing. All right, you can output a message and say something like, the stack is already empty, or you can't remove from an empty stack, whatever. Right? We do, because we specify that we're going to return a type marshmallow, we do need to actually return something. Nothing to return here, so we can return null. Okay, we need to do something. All right? So that handles if our stack is empty. So now we need to handle the next situation, which is if there's something actually in the stack. And so what I'm going to do is let me pull this. You know what? I think I can draw it. So if we've got a stack like this, where we've got first that points to this marshmallow object, and maybe this has a marshmallow or a fluffiness of 52. This one points to this marshmallow, which is 36. This one points to this marshmallow, which is 20. And this one points to null, because it's the last one on the list. If this is our stack, what we want to happen at the end, afterwards, is we want first to point to 36. 36 still points to 20, and 20 still points to null, with 52 being gone. This is what we want it to look like afterwards. So in order to achieve that, what do we need to do? Yes?
Set a temporary variable to keep track of the first one.
Good. So we'll set a temporary variable here and have it point to 52. This will be like step 1. This is so that when we change the reference from first to point to 36, we don't lose access to 52. If at any point in time we don't have an arrow pointing to 52, which is our reference, if we don't have something pointing to 52, we're going to lose it. We can't ever get it back. Okay? Garbage collection is going to come by and pick it up, and we will never be able to access it again. So because we want to return it at the end, we need to keep a temporary reference to it. So good job. Now, once we do that, how do we handle moving the first reference from 52 to 36?
Get next.
Good. Okay. So we're going to accomplish step 1 by saying temp equals first. And we're going to accomplish step 2 by saying first equals, because we want to change the first reference, and we want it to equal what first points to as its next reference. First dot get next. Okay? Questions on that? Now, if the only thing that's in the list is the last object, so if we only have one object in the list, and we say first dot get next, that's going to get us null, which is what first is going to reference. So that's good. Okay, so this handles our situation even if there is only one object in the list. Okay? So step 1, let's create a temporary variable. It's a type marshmallow, and we'll set it equal to first. So create a temporary reference to the first marshmallow so we can return it at the end. Okay. Update first reference to point to first next for the second marsh. Questions on this? Does this make sense? Are we starting to get a little bit more comfortable with this reference shifting that we're doing? This is going to be really important. And this type of coding is the type of coding that you will get into much, much more the more advanced stuff that you do. Okay? It's really important to know how to do this. This isn't something that's going to go away. Now, the ultimate test to see if this works is to run it. So let me save this, pop back over to our driver, compile, got an error. We're missing a return statement. We did a good job of creating the reference, but we never returned it. So we'll return temp. Yes, sir? Very good. Yeah, we got to update the size. Very good. Recompile, run it. We've already got our stack up here. So let's go ahead and speed it up. Let it add the 1, 2, 3, 4, 5 objects. I'm going to pause it here. Now let's go a little bit slower as we go into the, we pop down here to the remove method section. So we're going to loop through 5 times and remove all 5 of these marshmallows. Let me extend this out so we can see.
Wow, that's not very close.
No, this has probably been left out for a long time. It's reduced down to a single grain of sugar. All right, so we check to see, is it empty? We're not empty, so create a temporary reference to the first object in the list. This is going to, if you notice right here, when we look up at this, there's only one arrow pointing to marshmallow 12. It's first. So if we adjust what first holds, we're going to lose reference to 12 and we won't be able to return it at the end. That's the point of the temporary variable. So when we do this, notice now we have this local variable that points to 12. So we won't lose access to this because we're getting ready to change what first points to. Next line of code, remember, we read these assignment statements right to left. So before we can assign it to first, we have to first get this. So we're going to call first.getNext, which is going to get the marshmallow that first points to, which should be 76. So we call getNext, it returns 76, and then we set first equal to that. Okay, so we assign 76 to first, and this is what we get. Again, 12 still references 76, 10 now references 12. Update the size drop down to 4, and we return 12, and then we output it. We see the output will be shown down here after we call the toString method. So we output 12, which is what we expect. Okay? I'll let it play to run the rest, and we see how these get popped off, adjusts, and we're back to where we started. Any questions on this?
Good timing.
Is that like the old Batman, like Adam West?
That's perfect.
Will you call me old if I tell you I remember watching that on TV? Is this still on? Yes, you'll call me old?
No.
You have a question?
Oh, no. I do have a question, because I mean, just thinking about this theoretically, it's kind of been hard for me to wrap around. So with the set next, how does it know, like especially when you're removing a value, that the next value is then moved from the, like, I especially think about this with removing it, when you're talking about the list, because I'm thinking in terms of arrays, with the next value in the set next or get next method, how does it know that it has to move back to the previous value that it used once you removed the value in front of it, like the one that was the next value? Because like without an index, you know.
So what's happening is it knows by storing a direct reference to that object. Okay, and so if you look, and it might be easiest to look at it here. Let's run this again in the canvas. And I'm going to let it populate all 5 objects. So if we look at what's happening here, all of these boxes right here, like this box for first, these little boxes here on each of them, and these are all marshmallow objects. This little box here, these are the next references. Okay, and so when we're talking about how do we know, or how does it know what to update, all that we are doing is we are simply assigning it the memory location that we want to update it to. Does that make sense now?
Yeah,
okay. And so that's how we can get away with not having an index to do it. So as we remove, and if we walk through how this works, when we remove and we get to this first.getNext, it returns it. We say first, which references 42, this marshmallow, get next. So it goes to its box. Its next reference actually holds the memory location of this marshmallow. Okay? So when we assign first to that, it knows to point to this by simply taking whatever's in this box, which is the memory location of this. So instead of first pointing to marshmallow 42, it now points to what 42 pointed to, which was 55. So all that we're doing is we're just shifting and passing memory locations to objects. And in our case, those are marshmallows. So first simply just points to what first next pointed to. Okay, that's all that is doing, is just shifting it. So when you're looking at it like this, these arrows represent reference variables or pointers. Did that answer your question?
Yes, it did, actually.
Okay. Okay. Any other questions on this? Okay, so this wraps up stacks. Okay? And this wraps up the last data structure that we're going to talk about before we get to your midterm. Okay, which is coming up soon. Okay, so we've got some review and that sort of thing coming up. Which we'll talk about at the end of class today. But like I mentioned at the beginning of class, I do want to show you a couple examples and a couple coding examples at that about how stacks are used. So before I forget, because I forgot last time, I want to go ahead and put these up on Canvas now so that you guys have access to them, okay, for studying purposes and that sort of thing. All right. Let's switch over here. Oh, let's take a look at this game. All right, so this is a game in progress. We started this at the beginning of the semester. It is a very simple game. We start it. It's a 2-player split screen game. All right. Player 1's on this side, player 2's on this side. Player 1 can click on their cannons to shoot marbles. Player 2 can use the arrow keys to shoot marbles. Player 2 cheats a little bit. You can see nothing happens when you win. We're working on it. But here's the point. You'll notice that there's the potential for a rather large number of marbles to exist. Especially player 2 gets a little trigger happy. Okay, they can shoot a lot of marbles. All right? And I mentioned last class that it's really expensive to create or instantiate new objects. So what we don't want to do is every time we shoot a cannon, we don't want to create a new marble. That's bad news. Okay? Now, in a game like this, it would be fine. We're not pushing any graphical or processing limits with this game. Okay? But still, the theory or the principle applies. If we're running like a legitimate game that's doing a lot of stuff, whether it's some action game where we're shooting arrows or boulder or whatever it is that we are creating over and over again, we don't want to simply create them on the fly. All right, we want to pre-cache those, create them ahead of time, and the best data structure for maintaining those is a stack. Okay? So let's kind of look under the hood and see what's happening. All right, so if we look at this, when the game starts, and this game's made in Unity, but we're not going to get into a bunch of stuff. When the game starts, you can see that we start with 4 marbles. All right? And as I run this, right now, and it's hard to see on the projector, but they're grayed out. You guys see them grayed out? If I shoot a marble, notice how it pops up again. Okay? and then it disappears. Okay, I don't know, can you guys see that on the projector? Okay. If I shoot one, and then I shoot another, and then I shoot another, see how they appear? So what's happening is, these marbles are on a stack, and we're going to look at the code in just a second. Every time I need a marble by shooting a cannon, it pulls one off of the stack, attaches it, and shoots it. Now, when I'm done with the marble, it puts itself back on the stack. And again, we'll look at that, how that happens in a second. So if I shoot a marble, let's actually look at what's happening. So I pause the game. This marble gets shot. It's going to fly under this, hit the back wall, hit the ground, and then what we've created underneath, which you can't see, I'm going to hide this field. We've created this little ramp system. And this ball is going to hit here, roll down the ramp, very slowly, roll down the ramp, and hiding underneath is this invisible box. And when the marble collides with the invisible box, poof, it goes back on the stack. Okay? Now, you can't see that because the field's covering it. But that's what happens. As we continue to shoot marbles, so if I shoot 4 marbles, and then hide the field, as those marbles fall, they're simply going to get added back to the stack. Now, notice right here, 1, 2, 3 marbles, all 4 are active. As they hit this, they're going to get deactivated and put back on the stack, and they're going to go to gray. Okay? So that's how we reuse them. If I shoot another set of 4 marbles, it's going to be the same 4 marbles. So we're not constantly creating new marbles. Yes?
What happens though when he gets trigger happy and he shoots more than 4 marbles?
What do you think? What would you...
It creates another one?
Creates another marble. Yeah. So, and the idea here is we should probably start with about 30 or 50 marbles. So that you don't really hit that unless some crazy stuff is going on. The way it's set up now is it will simply create a new marble if we run out of marbles. So if we call pop and there's nothing to pop, it'll create a marble and then pop it. And in fact, the issue that we ran into is if we tried to create a marble at this exact moment that we needed it, it would still crash. And so what we did is, and the reason for that is, the process of creating a marble took longer than we needed it to. So basically it's like, okay, we need a marble, but before I took the marble and attached it, I didn't have the marble. And so we create a marble when there's only 1 left, I think. Or so when there's only 1 left in the stack, so we can actually create a new marble. So let me show the field again. Let me show the field again. Go back to our game. You notice down here, these marble clones are being created. And they eventually will get put on the stack as they get deactivated. Okay? Make sense? Let's look at the code. Now, in this situation, we use a built-in stack. Okay. Can you guys see this? It's kind of hard. We use a built-in stack. How many of you have used ArrayList before? Okay. When you use an array list, you use these angle brackets. Okay. And the reason you set these up is, let's take the marshmallow stack that we created a second ago. Can we put anything else onto the stack besides a marshmallow? No. Because if we look at the code for our marshmallow, we specify when we go to push an object, it better be a marshmallow, because that's what we said. And when we pop it, it better be a marshmallow, because that's what we're returning. And in practical use, that's great, as long as we're messing with marshmallows. But I can't take that stack and move it to another program and have it work. I can't take that code that we wrote and move it here and have it work for my marbles without changing the code. And that would make all of the stacks not very user-friendly. And so what they did is they came up with this concept called a generic. And when the data type is defined, instead of defining it for a specific type, like a marshmallow, they define it with a generic type, typically called T. And then, when you create the data structure, when you instantiate it, instead of specifying, okay, we're just going to create the structure, we say we're also going to specify what goes in the structure, which is what it goes in those angle brackets. Array lists use the same thing. So when you use an array list, you have to, in angle brackets next to the word array list, specify what type you're putting in it, so that it knows, instead of it being a generic marshmallow, it knows what specific type you're putting in. And we do the same thing here. So in this situation, we are actually adding to the stack a script that manages the marbles, which is a script on each of the marble objects. Okay. And again, this is the default implementation stack. It's part of, this is C#, which is almost identical to Java. You look at this, it looks a lot like Java. So here, marbles equals new stack. If I go to Marble Manager, what happens is when the game starts, the way this is set up is the marbles will actually add themselves to the stack. Okay? There is and you'll get into this as you take more advanced programming classes. You'll learn about design principles and different ways to organize your code. But this is set up as what is called a singleton, which is it forces a single instance of something throughout the duration of the program, which allows us to access it with a static reference. So I have a single script called Game Manager, which is the equivalent of a driver. And on that, I have our marble stack. Okay. Notice, what's the name of the method? Push. And there's no add, so you have to know what it's called, push. So what's happening here is when the game starts automatically called, this is equivalent of like main, I call add self to stack. This is the script that's on each marble. So we first deactivate the game object, which makes it invisible. That's what makes it gray. And then we get access to the stack, and we simply add itself to the stack. Make sense? This is when we actually shoot the marble. The last thing I will show you, this is the script that's on that little green rectangle that we saw at the bottom of the ramp. When it collides, we simply grab access to what it collided with, which will be the marble, and then we call add self to stack. So it's just going to add itself back to the stack. Very simple process. When we go to shoot, fire cannon. If there's only one marble on the stack, then we're going to instantiate or create a new marble, which will automatically add itself to the stack. Right? Grab a temporary variable, pop. So we're popping it off of the stack, and then we shoot the marble that we popped off. Okay. Questions on this? Good? So that's an example of using the built-in stack. The semester before that, we created a game. Sometimes our games get a little bit out there. Just like when we talk about, well, what do we want to put in our data structures? We came up with marshmallows. When we create games, sometimes similar things happen, where we just kind of let the ideas take us wherever they are. And so, this semester, the game that was created was, I forget what we called it, Color Box Creative. You are a sugar cube that has escaped, and you are trying to jump across a series of colored platforms to prevent yourself from prevent yourself from falling into this steaming cup of tea. Don't laugh.
Go on.
It's a thing. So, you can see that there's a series of platforms. And you're going to jump across the platforms. But the trick is, when you land on the platform, your color has to match the color of the platform or the platform breaks and you fall into the tea. So you can change your color from red to yellow to green to blue by pressing 1, 2, 3, 4. Okay? So when you land, your color has to be the same or it messes up. So, I'm terrible at this game, but I will play it just for a second.
This stuff's trippy.
What's the yellow? Oh, okay. So if I don't have the right color, and then I fall into the tea. Uh-oh. Ooh, skills. Now once you're on the platform, you can change whatever color you want.
You can change while you're on the platform.
Yep. Oh. All right, but here, so what you guys want to do.
Is it infinite platforms?
Yes. So what we have here, and this is how those endless runner games that you've all never played. So they work. So we have essentially an endless number of platforms. Now that doesn't mean that when the game starts, we just pick a really high number and say, okay, let's just create 1 billion platforms and hope they're not better than that. Okay, that's not how it works. What we do is we simply create a set of platforms. In this case, it looks like we have 15. And then we just reuse them. As a platform leaves, as it goes behind us, we simply despawn it or deactivate it, throw it back on the stack, and then when we need another platform, we take it and we throw it on the end. Change its color, change its size, all that sort of thing. We can watch how that works here. So, using a similar design, we have a platform despawner, which is another invisible box back here, that as our platform, let me disable gravity. As our platform collides with that box, it disappears. Okay? When it disappears, a new one gets added to the back. It just happens to be the same color, but it gets randomized. Right? So we can see, get the whole thing in view here. I've got to keep moving the player up and cheating. Once one platform goes away, like once this blue one despawns, another one's going to get added back here behind the red. Okay, see how it worked? And again, it just so happened to be the same color. But this is how we can reuse the same set of platforms. If we look at the code, in this situation, we actually coded our own stack. Okay, we didn't use the default one. Does this code look familiar? Push, pop, platform temp equals first, first equals first dot get next. return temp. It's the same exact code that we just wrote for our marshmallows. It's the same code that we use in this game. So, on one hand, and does this look familiar? A little message that says something happened. On one hand, I want you guys to know that the code that we write in class, you know that it's really basic. Okay? And the code that we are writing to create a stack of marshmallows, you're not going to do anything really cool with that. But at the same time, I want you to understand that even though the projects that we do in here are really basic, the code is the same as what you see in an actual game. Now, sometimes stuff gets added to it, and there's a little bit more here, but it's the same underlying principle, adding and removing to it. That makes sense? Any questions on it? All right, let's stop here.